We will try to solve this differential equation using Laplace transforms. First, use the fact that y double prime's Laplace transform is s squared ys minus sy0 minus y prime 0, where this capital Ys is the Laplace transform of y itself. Okay, so if we use this formula, here's what we get. The first y double prime will be replaced by this as written above, and then because y changes to capital Y of s when you take the Laplace transform, you have capital Ys. And on the right side, t transforms as 1 over s squared. So this is what you get after Laplace transform. Now we plug in the initial conditions, and this is what you get because y of 0 is 5 and y prime of 0 is 2. And then you can collect the y of s together. So it's s squared plus 16 times y of s. And the ones that do not have y of s, you can move it to the other side. Now, the first stage is to solve for capital Y of s. So we divide by s squared plus 16, and the first term will be divided by s squared plus 16, whereas the second one will again be divided by s squared plus 16, and this is our capital Y of s. You feel like you've solved something at this point, but you really didn't, because the original question is for y of t, the lowercase y of t, not capital Y of s. So you have to figure out how to go back to y of t once you get this. So let's look at the following. We have this Laplace transform, and I need to change that into the following partial fraction expansion. And the partial fraction expansion is almost like what you've learned in Calculus 2 for integrals, except there's one minor difference, that when you have a quadratic like this, make sure that you have it as completed squared form. Here it's already in completed squared form. And also write the constant term as something squared. And what you want to do is, instead of writing as plus b, you want to write down a times whatever this is. In our case, it's just s, but sometimes you have s plus something, and in that case, you have to have the same thing here. And also, whatever this number is, you have to put it in front of b. This will later help you in finding the inverse Laplace transform. Okay, and you also learned in Calculus 2 that if you have something to some power, then you start from the lowest order and then you increase until that power. So if this was s cubed, then you would have c over s, d over s squared plus e over s cubed. Okay? Alright, so this is our partial fraction expansion. Again, just look at all the factors. S squared plus 16, I wrote it as s squared plus 4 squared, so that's one factor. Because this cannot be further factored, this needs to be there as a single one. And when you have a quadratic denominator, you need to put something s plus another number. But as I explained earlier, it's slightly different for the Laplace inverse transform case. Okay, and then for the other ones, other factors, whenever you have a power, just start from the lowest power and then move upwards. Okay, so hopefully that made sense. Let's move on. What I want to do is, because s squared plus 16 is the biggest denominator, or the least common multiple of all the denominators you see here, I'm going to multiply that to every term that we see. So you see, this is multiplied the first one, this is multiplied the second one, this is multiplied the third, fourth. All of these are multiplied by s squared plus 16. And the reason you want to do this is, by doing this, you get rid of the denominators, so it's a lot easier to handle. So you see a lot of cancellation. S squared plus 16, s squared plus 16, they cancel. This entire thing cancels. These two also cancel. S squared divided by s will just leave you with just s. S squared will cancel. So after all these are canceled, you have a very simple equation to work with. As you can see, it's exactly what's left over after cancellation. Okay, so that's what I wrote down. Now normally I like to do plugging in numbers and just comparing the two sides and finding A, B, C, except that for this case there isn't any good number to plug in except s equal to 0 might get rid of A, B, C, and it'll tell you what D is, but apart from that there are no good numbers so that a lot of these disappear. So in that case I have no choice but to just expand this, the left side and the right side, and simplify. And it turns out that the expansion is not too bad. So s squared times s is s cubed, s squared times 2 is 2s squared, s squared times s is as cubed, 4b s squared, cs s squared is cs cubed, cs times 16 is 16cs, d times s squared, 16 times d. And then you want to organize the right side by the powers, so as cubed and cs cubed adds up to become a plus c s cubed. And then I also see s squared terms here and here, so you put them as 4b plus d s squared, and then 16cs and 16d. And if you compare this with the left side, all the coefficients should be matching because I need these to be equal as functions. Two polynomials are equal as functions if all their coefficients match. So I know that 5 must equal to a plus c, 2 must equal to 4b plus d. There's no s term on the left side, so 16c must be 0, and 16d must be 64. So you have the system of equations, which is not that hard to solve because immediately you see that c must be 0 from here, right? And then if you divide by 16, you get d equals to 4. Plugging in c equal to 0 here gives you a equals to 5, and plugging in d equals to 4, subtracting 2 minus 4 is negative 2, and divide by 4, you get b equals to negative 1/2. So you have these numbers, which can now be plugged back into the original form. And therefore, this is what we get. We get that y of s, which was found to be this one, can now be written in this format. And therefore, y of t, which is the Laplace inverse transform of this, and you can rewrite it as 5 times s over s squared plus 4 squared, right? And then negative 1/2 times 4 over s squared plus 4 squared, and this is gone, and then you have 4 times 1 over s squared. And once you write it in this form, you now see why we wanted the original form as as plus 4b, because once we factor the negative 1/2 out, this is exactly the Laplace transform of sine 4t, and this is exactly the Laplace transform of cosine 4t, and this is the Laplace transform of t, so that's what you get as the answer.